Good morning, class. We are looking at exam 3 review, chapter 3, differentiation rules, chapter 4, application of differentiations, section 4.4, indeterminate forms and L'Hopital's rule, 4.5, summary of curve sketching. Section 4.4, indeterminate forms and L'Hopital's rule. Limits of the following forms are indeterminate forms. An indeterminate form of type 0 over 0, infinity over infinity. Examples. Limit of ln x over x minus 1 as x approaches 1 is 0 over 0 if you plug in, because you get ln of 1, which is 0, and 1 minus 1 is 0. Limit of ln x over x minus 1 as x approaches infinity is infinity over infinity. L'Hopital's rule. Suppose f and g are differentiable and g prime is not equal to 0 on an open interval I that contains a except possibly at a. Suppose the limit of f of x as x approaches a is 0. The limit of g of x as x approaches a is also 0. Or limit of f of x as x approaches a is positive or negative infinity, and limit of g of x as x approaches a is positive or negative infinity. Then the limit of f of x over g of x as x approaches a, we can replace it and we say it's equal to the limit of f prime of x over g prime of x as x approaches a. Of course, if the limit exists. By the way, we don't want to mix them up with the quotient rule. You differentiate the top, you differentiate the bottom. In other words, the limit of f of x over g of x as x approaches 0, as x approaches a, if you plug in and you get 0 over 0 or infinity over infinity, then you can use L'Hopital's rule that indicates it's the same as taking the limit of f prime of x over g prime of x as x approaches a. So that's called L'Hopital's rule. Also, we have indeterminate products, indeterminate form of type 0 times infinity. We rewrite the product fg as a quotient fg equals either f over 1 over g or g over 1 over f y, because the only way to use L'Hopital's rule is to get to 0 over 0, infinity over infinity, and then it can be used. For example, we're going to look at the first one that we just mentioned. Obviously, you plug in 1, you get ln 1, which is 0. 1 minus 1 is 0, so you get 0 over 0. First, you show it's 0 over 0. Then you use L'Hopital's rule, which says I'm going to differentiate the top. I get 1 over x, and the bottom is 1. The notation that is used, h, either in this format or in this format, equal sign with h at top. You're telling the reader you're using the L'Hopital's rule. Simplification of this expression is 1 over x, and the limit of 1 over x as x approaches 1 is obviously 1. I want to look at an interesting example where L'Hopital's rule has to be used repeated. First, if you plug in 0, what do you get? Let me quickly show you. You get e to the power of 0 minus e to the power of 0 minus 0. You get 0 minus sine 0. And I hope you see that e to the power of 0 minus e to the power of 0, that means 1 minus 1, that is 0. Sine of 0 is 0, so you get 0 over 0, which means you can use L'Hopital's rule. Using L'Hopital's rule means I'm going to differentiate this, which is itself, minus I'm going to differentiate this, which makes this negative times negative positive e to the power minus x, and this gives me negative 2. I'm going to differentiate the bottom 1 minus cosine x. Now, if I replace the x with 0, the numerator is 1 plus 1 minus 2 is 0. 1 minus cosine of 0 is 1, also 0. 0 over 0, which means I am going to use L'Hopital's rule again. So differentiate, this one is e to the power of x, this one is minus e to the power of x, minus goes away, and negative cosine gives you positive sign. Plug in. You get e to the power of 0 minus e to the power of 0 over sine of 0. 1 minus 1 is 0, sine of 0 is 0. Again, 0 over 0. Again, we can use L'Hopital's rule. This gives itself the negative and negative plus e to the power minus x, sine gives you cosine. Now let's plug in. So we get e to the power of 0 plus e to the power of 0 over cosine of 0, which means e to the power of 0, e to the power of 0, 2 over 1, or simply 2. So after applying L'Hopital's rule a number of times, it actually works. And that's the idea. Yes, you can use that repeatedly. What about this case? Let's plug in pi over 2. One minus sine of pi over 2 over cosecant pi over 2. I'm going to change this to 1 over sine pi over 2. As you know, sine of pi over 2 is 1, so the numerator is 1 minus 1, 0. Sine of pi over 2 is 1, so 1 over 1 is 1. So the answer is 0 over 1 equals 0. If you use L'Hopital's rule, you will end up with the wrong answer. So first you have to show it's 0 over 0 or infinity over infinity before you can use the L'Hopital's rule. And that is extremely important to understand. Yes, you can use it when it's justifiable. Limit of x squared plus x minus 6 over x minus 2 as x approaches 2. What we did before, what we are going to do the same thing here. First, we're going to check it. And when we check it, we notice we get 0 over 0. If you plug in 2, you get 4, and 2 is 6 minus 6 is 0. 2 minus 2 is 0. And so because it's 0 over 0, it's an indeterminate form. So what did we do before? We did the factoring. Because x is approaching 2 and x minus 2 is a problem, you're hoping the top has a factor of x minus 2. It does. It's x minus 2 times x plus 3. And now if you plug in, you get 5. This is what we did before, and it works always. Also, you can use, because it's 0 over 0, you can use L'Hopital's rule, which means the limit as x approaches 2, we're going to differentiate this, we get 2x. This one is 1, this one is 1, everything else is 0. So this is using L'Hopital's rule. And now if I plug in 2, I get 4 and 1, 5 over 1, or simply 5. As you can see, we have two choices here. In some cases, we don't. The limit of ln of square root of x over x squared. If you plug in, you get ln of square root of infinity over infinity squared, which is infinity over infinity. And therefore, we can use L'Hopital's rule. To do that, we are going to change this to x to the power of 1/2, and therefore it becomes 1/2 ln x over x squared. Now we are going to differentiate the top and the bottom because we've shown that it's infinity over infinity, right? So when you differentiate ln x, you get 1 over x. When you differentiate x squared, you get 2x. 1/2 times 1 over x over 2x is 1 over 4x squared. I'm assuming everybody is okay with that. Let me just quickly show you. This is 1 over 2x over 2x, and this is over 1, these two at top, these two at the bottom. And now if you plug in infinity, obviously the answer is 0 because you get 1 over infinity. So it's very straightforward, everybody. The limit of x times ln x, if you plug in 0 from the right, you get 0 times ln of 0 from the right, which is negative infinity. Again, I want to make sure we understand why this is negative infinity because we should know the graph, and that's the vertical asymptote, remember that? And so all you have to do, take one of them down and make it look like infinity over infinity. By the way, if it's 0 times infinity or 0 times negative infinity, doesn't matter. You take one of them down. Whether it's infinity over infinity or negative infinity over infinity, it is still indeterminate. So it's easy to take the x down. And now if you plug in, of course, the top is negative infinity, the bottom is positive infinity, which is still the format that you want, this one. So we are going to use the L'Hopital's rule, which means we're going to differentiate the top. We get 1 over x, and the bottom is negative 1 over x squared. I guess by now everybody knows that, just for the sake of argument, if you want to differentiate 1 over x, this is what you get, which is negative 1 over x. And I hope you see that you can simplify this. Let me rewrite this so it becomes clear you're dealing with a complex fraction. So you multiply these two, get x squared, and multiply these two, you get minus x. So the answer is minus x. And if you plug in, so the limit of negative x as x approaches 0 from the right is simply 0 when you plug in. Let me erase my work so we can continue. Now, the limit of square root of x times e to the power of negative x over 2. As x approaches infinity, this is square root of infinity, which is infinity. And e to the power of negative infinity is 0. Again, I want to make sure that you understand what's happening here. E to the power of minus 1/2 x is 1 over e to the power of positive 1/2 x. When x goes to infinity, e to the power of 1/2 x goes to infinity, 1 over that goes to 0. That's the idea. And so it's 0 times infinity, and the methodology is to take one of them down. Obviously, you want to take this one down and make it with positive exponent. And at this point, if you plug in infinity, you get infinity over infinity. So we are going to differentiate each piece. Square root of x, hopefully we know it's 1 over 2 square root of x by now, or change it to x to the power 1/2. So it's 1/2 x to the power negative. This one is e to the power of 1/2 x, 1/2 x. So it's itself times 1/2, okay? And since we're going to go this way and that way, we are going to drop, can drop the 2 here. Okay, so in essence becomes 1. So 1 times 1 goes up. This, okay. So the extremes, you put them at top, and the means, you multiply them, you put them at the bottom. As x goes to infinity, so does the denominator, infinity times infinity, so this is 0. Indeterminate differences, the type infinity minus infinity. Try to convert the difference into a quotient by using a common denominator or rationalization or factoring out a common factor so that we have an indeterminate form of 0 over 0 or infinity over infinity. Normally, one of those methodologies, for example, common denominator will do the job. Now, when x approaches 0 from the right, and you can refer to the graph of these two functions, it becomes infinity minus infinity. But even if you don't see that, cosecant is 1 over sine and cotangent is cosine over sine. And over here, I hope you see that when x approaches 0 from the right, sine becomes 0 from the right, okay? So this goes to infinity, cosine becomes 1. So both of them go to infinity. So infinity minus infinity. So this might make it easier to see. Anyways, take a common denominator of sine x, LCD, and now plug in. If I plug in 0, cosine of 0 is 1, sine of 0 is 0, and 1 minus 1 over 0 is simply 0 over 0, which indicates we can use L'Hopital's rule. So the limit as x approaches 0 from the right, the top, negative cosine becomes positive sine because 1 goes to 0, and sine becomes cosine. If you, of course, you can say this is tangent and tangent is 0. You can do that. Or if you plug in sine of 0 is 0, cosine of 0 is 1. 0 over 1 is 0. So you can do it that way. Or you can say this is equal to the limit of tan x as x approaches 0 from the right. Tan of 0 is 0. All right. The limit of ln of x to the power of 7 minus 1 minus ln of x to the power of 5 minus 1 as x approaches 1 from the right. I hope you realize if I put 1, I get 0, but in both cases, I get ln of 0 from the right. Okay. Why from the right? Because this is 1 from the right, so this is a little bit more than 1, this is a little bit more than 1. And ln of 0 from the right is negative infinity. So negative infinity minus negative infinity means minus infinity plus infinity. And that is indeterminate. So how do you fix that problem? We are going to go with logarithmic properties. So let me erase my work. We're going to use the quotient rule. Log of x over y is log x minus log y. All of them have the same base. So therefore, we're going to go from right to left, and this becomes ln of x to the power of 7 minus 1 over x to the power of 5 minus 1. All right. Now that we have that, we can interchange natural log and the limit. If we plug in 1, we get 0 here, 0 here, 0 over 0. So ln of 0 over 0. And this will tell us we can do L'Hopital's rule, everybody. So let's differentiate. Ln of the limit as x approaches 1 plus 1 from the right of 7x to the power of 6 over 5x to the power of 4. And this, if I plug in 1, I get 7. Over here, I get 5. It's precisely ln of 7 over 5. That's an exact answer. So it's important to know it's not necessarily 0. You have to go through the process to figure it out. Here's another example. The limit of secant x minus tan x as x approaches pi over 2 from the left. That means like 89.9 degrees. That's the ideal. And again, if you don't see what's happening, really the best course of action to change the secant to 1 over cosine and tangent sine over cosine. But each one is infinity. So we get infinity minus infinity because we should first notice secant goes to infinity, and so does tangent as x approaches pi over 2 from the left. And I hope you remember the graph. So you get infinity minus infinity. Secant is 1 over cosine. This is sine over cosine. We replace them. And over here, pi over 2, remember, cosine is 0. But pi over 2 from the left, we are in the first quadrant where every trigonometric function is positive. So it's on the positive side. Same thing happens here. Sine is 1, cosine is 0. And so in essence, you get infinity minus infinity. You can see it here. Take a common denominator, LCD is cosine x. And now if you plug in pi over 2, you get 1 minus, let me just do that, sine of pi over 2, which is 1. So 1 minus 1 is 0. And cosine of pi over 2 is 0. So we get 0 over 0, which means we can use L'Hopital's rule. We are going to differentiate the top and the bottom. This becomes minus cosine x, and the derivative of cosine is minus sine x. And you have a choice. You can plug in, first of all, negative and negative cancel each other. Cosine is 0, sine is 1, you get 0, or you might say this is the limit of cotangent x as x approaches pi over 2 from the left. And you should know this is 0. It's a common arc, everybody. Okay, pi over 2 is a common arc. And cotangent is cosine over sine. Which one is easier? I don't know. It's a trigonometric function in this format or in that. We also have indeterminate powers in this case. Several indeterminate forms arise from the limit. When we have the limit of f of x to the power of g of x as x approaches a, we may get the following: 0 to the power of 0. If the limit of f of x as x approaches a as well as the limit of g of x as x approaches is 0, we get 0 to the power of 0. If they are both in, one is infinity, one is 0, then we get infinity to the power of 0. And if the limit of f of x as x approaches a is 1, the other one is positive or negative infinity, we get 1 to the power of infinity or negative infinity. And so 1 to the power of infinity. Each of these three cases can be treated either by taking natural logs, let y be f of x to the power of g of x, call it a y, then take the natural log. If I take a natural log of this one, g of x sits in front by the logarithmic properties. Okay, these are the logarithmic properties I'm referring to. Okay, see, n sits in front. And therefore, we have the limit of ln y as x approaches a. If it ends up being something, let's make it up. Let's say it's k. Then the limit of what we want, y, which is f of x to the power of g of x as x approaches a, is e to the power of the same exponent, or you can show it is the case. But the fastest way, if this is k, this must be e to the power of k because we took the natural log and we are undoing it now. Or by writing the function as an exponential, if f of x is, if we have the function f of x to the power of g of x, and f of x can be replaced by e to the power of ln f of x, right? Take a look. E to the power of ln x is the same as x. So e to the power of ln f of x, let me just, this, everybody, is the same as f of x, okay? So now you have e to the power of ln f of x to the power of g of x. This is the power rule of exponentials. That means e to the power of this times this. So we put this one first. G of x times ln of f of x. In either method, we are led to the indeterminate product g of x times ln of f of x. G of x times ln of f of x, which is of the type 0 to infinity or infinity times 0, and we know how to handle this, right? So that's what's going to happen. Example. The limit of 1 plus sine for x to the power of cotangent x as x approaches 0 from the right. Again, reminding you of the L'Hopital's rule. And so when x becomes 0, sine becomes 0. So this is 1. And 0 from the right cotangent goes to infinity. Again, has got to do with the graph and knowing the information about common arcs, cotangent of 0, okay? Cotangent of the 0 is either negative or positive infinity. On the right side is positive, and the graph of cotangent looks like y equals almost minus x cubed. So it's 1 to the power of infinity. So we are going to give this a name y because it's easier to deal with. Y is this piece, the function 1 plus sine 4x to the power of cotangent x. So if I take the natural log of both sides, ln of y is ln of the right side, and then I can put the cotangent x in front using this power rule, if you will. And so cotangent is 1 over tangent. So I'm going to put this 1 over tangent x. The reason, just right here, I want you to see that when x approaches 0, this is ln of 1, because sine is 0, ln 1 is 0, and tan of 0 is 0, it becomes 0 over 0, that's 1. So now we're going to take, instead of taking the limit of this piece, okay, we're going to take the limit of ln y. So the limit of ln y as x approaches 0 from the right is the limit of this expression as x approaches 0 from the right. And as I mentioned, if I change this to 0, I get 1 plus 0. If I change this to 0, I get 0. I get 0 over 0. Which means I can use L'Hopital's rule. The idea is to make sure L'Hopital's rule is in order. And we can use L'Hopital's rule here because it's 0 over 0. So having said that, we are going, let me erase my work so it becomes clear. So we are going to say by the L'Hopital's rule, this is the limit as x approaches 0 from the right. Take the derivative of the top, take the derivative of the bottom. The top is a natural log, everybody. So 1 over 1 plus sine for x, and then times the derivative. The derivative of sine is cosine of 4x, and then times 4. So 4 cosine 4x. And then the bottom, tan x, the derivative is simply secant squared x. Please don't mix it up with the quotient rule of differentiation. And you can change it to a simple fraction. It's a complex fraction. We just plug it. If you plug in 0, cosine of 0 is 1. Let's see. Sine of 0 is 0. Secant is 1 over cosine. So this is 1 over cosine, which is 1 over 1, which is 1 squared. So you have a 4 over 1, the whole thing divided by 1, and I hope you see that it's 4. And therefore, your answer is simply to the original question, e to the power of. But just to justify it and remind you, again, right here, you should know it's e to the power of 4, everybody. Here's what we had as the original one, limit of y as x approaches 0 from the right, which is limit of e to the power of ln y. That's the reason. Y and e, let me just, y and e to the power of ln y are the same. Therefore, the answer is e to the power of, for the ln y, we got 4, so e to the power of. The second method for this case, and I'm going to leave it for you to do that, would be to change it to the exponential format. As an exponential format, reminding you f to the power of g of x means e to the power of ln of f of x to the power of g of x, or e to the power of g of x times ln of f of x. Therefore, this piece is e to the power of ln of 1 plus 4 sine x to the power of cotangent x. That means e to the power of cotangent x, ln of 1 plus 4 sine x. If you want to differentiate this, if you want to take a limit of this expression, showing that this expression is the same as this expression. And now you can take the limit as x approaches 0 from the right of that expression. If that helps, again, that's absolutely up to you, everybody. Okay, I think that's pretty straightforward. Let's move on. 4.5 summary of curve sketching. Definition: vertical asymptote short VA, horizontal asymptote short HA if you have a rational function, f of x in the form of n of x over d of x, where in the numerator is a sub n x to the power of n all the way to a sub 0, which means n is the degree of the numerator, and the denominator is b to the b sub m x to the power of m all the way to b sub 0, which means m is the degree, where n and d are both polynomials and d can't be 0, and the domain is all real numbers except what makes d of x 0. This is the definition of a rational function. So vertical asymptote has the equation x equals a if the x equals a if the limit of f of x as x approaches a from the left is negative infinity or positive infinity, or as x approaches a from the right is negative or positive infinity. The graph of a rational function if it crosses a vertical asymptote, it may intersect its vertical asymptote. And it's important to know we have to have the simplified version. That means you must put this in lowest term, no common factor. If there is a common factor between the top and the bottom, it creates a hole. Then vertical asymptote, the easiest way, set the denominator equal to 0 after we simplify. Now, definition in calculus, limit of f of x as x approaches a, or a from the left or from the right, is it either negative or positive infinity, then VA has the equation x equals. You can go with the definition, set the denominator equal to 0 as long as it's in its lowest term. Horizontal asymptote HA as for the function y equals f of x has the equation line y equals L if the limit of f of x as x approaches negative or positive infinity is L. The graph of a rational function may or may not cross a horizontal asymptote. HA has the formula in precise definition, limit of f of x as x approaches positive or negative infinity is L, then the line y equals L. Now, what about oblique, also known as slant asymptote, OA or SA? Y equals mx plus b. If the limit of f of x as x approaches negative infinity is mx plus b, or the limit of f of x as x approaches infinity is mx plus b. In other words, if you look at this expression, and the degree of the numerator is n, the denominator is m. If n is less than m, horizontal asymptote has the equation y equals 0. This is what we learned from pre-calculus. You can stick with that. If n equals m, then the leading term take over. They cancel each other. We get y equals a sub n over b sub n. If n is precisely m plus 1, that means the degree of the numerator is larger by only 1, you divide, either long division or synthetic division, becomes mx plus b and some remainder. Then this part, y equals mx plus b, is the equation of a slant or oblique asymptote, everybody. So that's pretty straightforward. All right, divide using synthetic division, express the answer as f of x over d of x equals q of x plus r of x over d of x. D stands for the denominator, 3x cubed minus 2x squared plus x minus 4 divided by x plus 1. All right. Division of a polynomial by x minus k. If the degree n polynomial p of x is divided by x minus k, then the quotient polynomial q of x has degree n minus 1. In other words, whatever the degree is here, because this has degree 1, this goes down by 1, obviously. If it's 10, the result should be the quotient should have a degree 9. That's the idea. The remainder r is a constant. Because this is degree 1, the remainder must be a constant. That means degree 0 and may be 0. The complete quotient for p of x over x minus k is written in this format. P of x over x minus k is q of x plus r over x minus k. In other words, if we look at this example, 3x cubed minus 2x plus 5 over x minus 3. This is the dividend. This is the divisor. You work it out, you get this answer, 3x squared plus 9x plus 25. This is degree 3, this is degree 2, this is the quotient polynomial. The remainder is a constant, plus 80 over x minus 3, okay? And so this is the remainder, this is the divisor again. So how do we work with this? If we want to go with the synthetic division, we are going to write the coefficients, and it has to be in descending order 3, negative 2, positive 1, minus 4, and this one we're going to put minus 1. By the way, if any of them is missing, let's say this was missing, you have to have a placeholder. You must put 0 there as a placeholder. So basically, you drop the first one. Then you multiply by negative 1. You get negative 3. You add these two, you get negative 5. You multiply by negative 1, you get positive 5. You add them up, you get 6. You multiply by negative 1 again, you keep on multiplying, and you get negative 10 when you add them up. And therefore, the answer is 3x squared minus 5x plus 6 with the remainder minus 10. So you write it in this fashion. 3x cubed minus 2x squared plus x minus 4 over x plus 1 equals 3x squared minus 5x plus 6 plus negative 10 over x plus 1, or you might say minus 10 over x plus 1. All right, we want to find all asymptotes. F of x is x squared minus 4 over x minus 1. Obviously, the VA x minus 1 equal to 0. So x minus 1 equal to 0, and you get x equals 1. Horizontal asymptote, we don't have anything. Why? The degree of the numerator is 2, the degree of the denominator is 1, it's larger. There is no horizontal asymptote. However, because the difference is exactly 1, we do have oblique asymptote. We are going to divide. Doesn't matter, long division or synthetic division, either way is fine. So long division, you divide the first one by the first one, you get x, and you multiply the x. You get x squared minus x. You subtract it, that means x squared minus x squared cancel each other, minus minus x, you get x. You bring the negative 4 down and divide x by x, you get 1. You multiply the 1, you get x minus 1. And again, you're subtracting, class. So you're subtracting. When you subtract, you get minus x and x cancel each other. You get plus 1 and negative 4, negative 3. That is your remainder. So we're going to write this as x plus 1 plus negative 3 over x minus 1. That's not what we want. We want the asymptote. Slant asymptote is this part, y equals this part, and that's the idea. Y equals x plus 1. Given the function, find the domain of f in interval notation. We are going to factor, and the numerator is fine. This is 2. If it doesn't work, you have to go with the quadratic formula. So it's very simple, x and 2x. And then you work on 12, 1 and 12, 2 and 6, 3 and 4. And you have to go with the trial and error until it works out. 4 and 3 work out because the product of these two is 8x, 3x, and the sum of those must be 11x. They do work. And so first and foremost, you drop the common factor. But it is important to know, even though you're going to drop the common factor, it doesn't make any difference. X can't be -4. And as far as the domain is concerned, X can't be -4 here. This one, X can't be -3/2. So you go with the original one. And in an interval notation, you're right, domain is -∞ to -4, union -4 to -3/2, union -3/2 to infinity. That's the way we do the writing. I hope everybody is fine with that. Let me erase my work. Find asymptotes as well as any holes. As far as holes concerned, if there is a common factor, there is a hole. Meaning, what is the difference between the graph of this function and this function? This function has no hole. But this function, because there's a common factor and says x can't be -4, at x equals -4, you plug in here, you can find the hole. So plug in -4 here. So the coordinates would be -4, and then 2 times that, -8 and 3 is -5. So 1 over -5, or you would say -4 comma -1 over 5. So 1, 2, 3, 4 on the left side, -4, and -156, -1. So somewhere here we have the hole. What about vertical asymptote? It's important to know not here, because we dropped the common factor here. 2x plus 3 equal to 0. Okay, 2x plus 3 equal to 0. X equals -3/2. That's the vertical line. What about horizontal asymptote? I'm going to remind you what we just went over. When you have a rational function, if n is less than m, horizontal asymptote y equal to 0. I've explained the rest of them already. So the degree of the numerator, 0. The degree of the denominator, 1. Therefore, y equals 0 is the horizontal asymptote, and you can't have both. Either you have horizontal asymptote or oblique asymptote, not both. Therefore, there is no oblique asymptote. Y equals 0 is the x-axis. So I put a dash line for that. Find the intercepts. Well, that means x is 0, find y, y is 0, find x. And I want to explain how a fraction works. Again, a fraction in the form of a over b is 0 if a is 0 and is undefined when b is 0. So x-intercept, that means y or f of x is 0. The numerator is a number, can't be 0. It doesn't have any. So x-intercept, none. Y-intercept, if I replace the x with 0, I get 1/3. Therefore, x-intercept is none because the numerator is a number. Doesn't matter, positive, negative, small or large. Y-intercept, 0, 1/3. So this is the x-axis, this is the y-axis, this is 1, so 1/3 is 1/3 of the way here, so 0, 1/3. Now, locate at least one point on each side near the vertical asymptote. And to do so, class, the idea is that here's the vertical asymptote. On this side, actually, you should know the graph looks like that, even if you don't locate it. But on this side, is it like so or like so? Actually, the whole indicates it should be like so. So let's go with easy points. If I choose -2 here, I get -4. With +3 is -1. 1 over that is -1. If I choose -1, I get +1, so I get 1. So these are the 2 points, -2 comma -1, -1 comma -1. Here's the graph, here's the graph. And we're done with the graph of this function. Sketch the graph of f of x equals x minus 1 over 2x plus 1. Let's go with the intercepts. X is 0, find y. Y is 0, find x. So x-intercept set y equal to 0. That means f of x equal to 0. That means y equal to 0. A fraction is 0 when the top is 0. In other words, x equals 1, we get 1, 0. Y-intercept means f of 0 means replace the x with 0, we get -1 over +1. So 0, -1. And so 0, -1. So we have those two pairs. Asymptotes, we start with the vertical asymptote. 2x plus 1 is 0. Means x equals -1/2. And it's a vertical line. X equals -1/2. We are taking each tick mark to represent 1/2. Horizontal asymptote, y equals 1/2. Y is that? Look at the numerator, the degree is 1. Look at the denominator, the degree is 1. So the leading coefficients 1 and 2. So y equals 1/2. And of course, if you have a horizontal asymptote, you can't have a vertical. You can't have a slant or oblique asymptote. Y equals 1/2. Now I want to add calculus. So I'm going to go with the derivative and the domain. Of course, the domain, first and foremost, 2x plus 1 equals 0, x equals -1/2. Domain x can't be -1/2, which means -infinity to -1/2, union -1/2 to infinity. So that's the domain. What about f prime of x? This is f over g, which means f prime g minus g prime f over g squared. So the derivative of the top is 1 times 2x plus 1 minus the derivative of the bottom is 2 times the top x minus 1 over the bottom squared. So we are going to simplify the numerator as follows. These two cancel each other and we get 3 over 2x plus 1 squared. Now, I hope you see that this is always positive as long as x is not equal to -1/2. Why is that? The denominator is something to the power of 2. It's always positive. And the numerator is positive. Positive over positive is always positive. The only time it can't be if the denominator is 0 and it's undefined. However, just to remind you of the first derivative test, if you put x going from negative to positive infinity. This is positive, everybody. And at negative 1/2, f prime is undefined. If you pick a number to the left of negative 1/2, the easiest number would be, let's say, -1. To the right is 0. And you plug in, and you see if you plug in 0, you get 1 squared. 3 over that is positive. If you put -1, the same thing is squared, makes it positive. So both sides is positive, okay? And what it means is it's always increasing. There is no extrema, there is no local max, local mean. And so it's always positive, the arrows up. So how do you write that? You don't write from negative to positive infinity. Rather, you write negative infinity, comma negative 1/2, union negative 1/2 to infinity. That's how you do that, everybody. It's important to understand that, okay? This is again for the information as far as extreme. Now we have the f prime as 3 times 2x plus 1 to the power of -2. Therefore, we are ready for f double prime. So I'm going to differentiate that again to get to f double prime. To differentiate that, I'm going to write f double prime is 3 times -2 times 2x plus 1 to the power of -2 minus 1 is -3 times the derivative of the inside, which is 2. And so we get 3 times -2, -6 times 2, -6, and put this in the denominator, make it positive exponent. We go with the number line, and again, f double prime equals 0, just like f prime of x doesn't give you any solution. F double prime doesn't exist, gives you x equals -1/2. So with the number line, from negative infinity to infinity, if you put -1/2 over here, it becomes positive, over here it becomes negative, because if you choose, as I mentioned here, for example, -1 here and 0 here, if I put 0 here, I get 1. Cube it is 1, and -12 over that is negative. If I put -1, I get -2 here, plus 1 is -1. Cube it is -1. Negative over negative is positive. Positive means concave up from negative infinity to -1/2. Negative means concave down from -1/2 to infinity. There is no inflection point. Why not? Because x equals -1/2 is not part of the domain, okay? So -1/2 is not part of the domain, it's undefined. Now, we have to always check to see if the function crosses horizontal asymptote. You set the function equal to the horizontal asymptote. Horizontal asymptote was 1/2. This function equals 1/2. We do the cross product. We get 2 times x minus 1 is 2x minus 2, and 1 times 2x plus 1 is 2x plus 1. As you can see, they are not equal because 2x cancels out 2x. Is -2 the same as +1? No, no solutions. That means they don't cross. Now, on the right side, is a vertical asymptote. On the right side, we have 2 points, and really this is the graph. So there's really not much to it. On the left side, is the graph like this or like that? You should really know it's like that because we don't have any more x-intercepts. But let's just pick an easy number. For example, let's say x is -1. If x is -1, everybody, negative So if x is -1, everybody, -1 and -1 makes it -2. 2 times -1, -2 plus 1 is -1, and the ratio is +2. So -1 comma 2 is here. Here's the graph, and we are done. This one, this one. And I hope you see that it's really not that big of a deal. Given the function f of x equals x plus 1 times x minus 5 over x minus 3, we want to graph it. So we're going to go through some process here, everybody. Starting with the domain. So basically x minus 3 equal to 0, x equals 3 must be excluded, so x can't be 3. How do you write it? Negative infinity to 3, union 3 to infinity. Asymptotes. Vertical asymptote, x minus 3 equal to 0, you get x equals 3. There is no horizontal asymptote. Why is that? So first of all, x equals 3 is this. Why there is no horizontal asymptote? If you multiply these two, you get x squared. 1 and -5 is -4x. 1 times -5 is -5. The degree of the numerator is 2. The degree of the denominator is 1. We don't have a horizontal asymptote. Instead, we do have oblique or slant asymptote. So we divide the top by the bottom, and let's quickly do it by the synthetic division. We have to put this in order. It is 1 minus 4 minus 5, and this is going to use +3 because it's x minus k. So you drop the 1. You multiply the 1 by 3, you put it here. 3 and -4, they add up to -1. You multiply the -1 by 3, you get -3. You add those two, you get -8. And so because this is degree 2, this is degree 1, this goes down by 1, becomes degree 1. So this is 1x, or simply x, minus 1, and this is the remainder. Pretty straightforward. And that means y equals x minus 1 is the equation of an oblique asymptote, and there is no hole. Now, I want to explain about the hole again. The hole happens if there is a common factor between the top and the bottom. There is no hole because there is nothing in common between the two. All right. So y equals x minus 1. You can pick up a couple of pairs quickly. I'll show you. Okay. And then maybe I'll put it here. Let's see. I put it here and I erased it, x and 1. Just erase my work. X and 1. If x is 0, you get -1. If y is 0, x you get 1. So that's how you graph it. And this is 10. This is 10. So roughly 1, 0 is here, 0, -1 is here. It may not be to scale, but it's close enough. Now we want to find the intercepts. Well, x-intercepts, we go with this. X-intercept, the top is 0. X equals -1, x equals +5. Okay. Fraction is 0 when the top is 0. And so the top is 0, x equals -1, x equals 5. That means -1, 0, 5, 0. Y-intercept, set x equal to 0. So this becomes +1 times -5 over -3. +1 times -5 is -5 over -3 is 5/3. So this would be -1, 0 somewhere here, 5, 0 somewhere here. And now we have 0, 5/3. So somewhere here, 5/3 is like 1 and 1/3. So there. locate at least 1 point on each side near the vertical asymptote. We already have 2 points here and 1 point here. We don't need anything else. To sketch it, basically, this goes through that, and along the vertical asymptote as well as the oblique asymptote. That's the graph. You can add calculus if you want. Doesn't do much.